Hey everybody, it's Alex with Engineering Applied. In this video, I'll be giving you a detailed overview of the motion constraints found within an Autodesk Inventor assembly file. If you want more easy to understand and practical content like this, made by an experienced engineer like myself, make sure you like this video, subscribe to the channel, and turn on notifications so you don't miss out on any helpful content like this in the future. If you're looking for a specific function, check the description for timestamps. And if you don't find what you're looking for in this video, make sure you check out the other videos in the Autodesk Inventor series playlist because I know you'll find exactly what you need there. Let's get started. Okay, everybody, so here we are in our assembly file. And so how this lesson is going to be laid out is we're first going to look at the rotation motion constraint, and then we'll look at the rotation translation constraint. So here I have two spur gears. I have the pinion, which is the smaller gear, and this drives the other gear. Okay, so this one will rotate, and then this will rotate as a result of this one rotating with it. Okay, so in this particular example, I went ahead and just brought in the gear geometry itself. There's nothing special going on here other than the two gears being brought into the assembly. Okay, and then I also positioned or mated some of their axis geometry to that of the origin in my design space. So what I'll do is I'll go through how I did that so that you can see how I created these mates and what mates I have in place to make this actually happen. Okay, so it's not just as simple as providing the rotational motion constraint. You have to set up the assembly properly so that you can make sure that everything is rotating as it's intended. Okay, so let's go ahead and pull in our pinion gear, which is the smaller of the two gears. So we're going to go to place. We'll go into the correct folder. I used the design accelerator to generate the geometry for the two different gears. Okay, so I specified the gear ratio and some other parameters that I wanted to use for this particular example. So we'll pull in the first of the two gears, which is the smaller one. Okay, and then I'll just go ahead and left click to drop it anywhere in 3D space because I'm going to manually create the constraints myself. I don't want to place it grounded at the origin because I want this to actually be able to move. So once I place the first one, I can go ahead and right click to go into my marking menu and press OK to drop it into place. If you're not familiar with placing components in an assembly, I encourage you to go watch that video first and then jump back into this one so that you have a strong foundation before proceeding on with this lesson. So what we need to do first here is we need to create a constraint set that sets this firmly in 3D space, but still allows for the rotation of this around its central axis, okay? So the first constraint that I'll go ahead and make here in this particular case is I'm going to tie the axis of the spur gear itself. So if you go into the origin folder of the spur gear, you can find the center axis, which is this Z axis, and then let's go ahead and mate it to that of the origin. Okay, so let's find the axis that corresponds properly with the origin, which is going to be the Z axis here in the origin. I'm going to left click on that and then let it snap into place. And when I hit apply, and actually let's go ahead and jump out because I want to show you how this can move still. So even though it's constrained to the axis, we can still rotate about that axis and it moves along that axis. In this particular case, I actually don't want this to be able to slide along that axis at all. So we're going to mate one of the faces to one of the planes of the origin. All right, so let's go ahead and create this next constraint. So we'll just make sure it's on mate. And we want to go ahead and mate this rear face to the XY plane that's associated with the origin. So we'll left click on that, let it snap into place. We'll click OK. And now you'll notice when I go to rotate this part, it only rotates about its central axis. It's actually not allowed to slide along the axis we initially constrained it to, which is exactly what we want. Now, the final setup constraint that we'll be applying to this pinion gear is an angle constraint between the XZ plane of the pinion gear itself and the XZ plane of the origin, okay? And the reason why we're doing this is later on, after we create this constraint and finish up the other elements in this assembly, we can come back and drive that angle constraint, which will drive the motion in the entire assembly. Now let's go ahead and create this constraint. So we'll go to constraint, click on angle, change this to a directed angle, and then let's go ahead and select the XZ plane of the pinion, the XZ plane in the origin, okay? And then let's go ahead and rename this. Let's change this to pinion, and then I'm gonna just put a note here that says drives assembly, okay? And I'm doing this so that I know which angle constraint needs to be driven to move these gears in the assembly. Now let's go ahead and click OK. And you'll see now in our model browser, we have that entity. It's that angle constraint that says pinion and that it drives the assembly, and currently is set to 0 degrees. We'll come back to this later and drive this so that we can move the gears together. But let me show you what this does before we move any further. So I right click on that. I can go down to drive, and then let's go ahead and set this angle to 720 degrees. It doesn't really matter. I just want a long rotation angle or a larger rotation angle so that you can see more of the rotation. And then we can come down to this little play button, and you'll see it rotates about its center axis. Now, when I move the mouse cursor around, it pauses the playback. So just leave your mouse alone and it'll go through a continuous playback, and you can watch it go around. And then at the top of this little window, it tells you the position, the current position relative to its starting point in that rotation angle. Now let's go ahead and pull in our other gear. So we'll go to place, pick up our second gear, drop it anywhere. We can right click to go into our marking menu and press OK. And then the first constraint I'm going to create here is just a flush constraint between this face and this face, because I want the gears to be perfectly in line with one another. So we'll go to constrain. We'll just leave it on mate. We'll click this face and this face, switch this to flush and hit OK. And then we can drag this away a little bit just to sort of reposition it before we apply our next mate. Now, since I always want the larger gear to be directly on top of the pinion, what I can do is I can constrain the central axis of the larger gear to the YZ plane with respect to the origin. Let's go to constrain. We'll click on the Z axis for this larger gear, and then let's click on the YZ plane. And you'll see it'll snap those two entities together and it'll center them up. That's okay. We can go ahead and click OK and then just move this up again. But the one thing I want you to notice is I can freely rotate this about its central axis. But the problem here is we can still drag it up and down. Now, ideally, when these gears are set up in the assembly, of course, you want them to have the proper center to center distance, which is dictated by your design parameters. So let's go ahead and do that now. Click on constrain, go down to the Z axis of the larger gear, and then click on the Z axis for the pinion. And when we do that, it snaps those two axis entities together. That's okay. All we have to do is set our offset distance, or our center to center distance in this case, into the offset field. So in this case, it's going to be 3 inches. So I'll type 3 there. And let's go ahead and click OK. Now that I've done that, the gear will freely rotate around its central axis, but it won't move up and down, and it won't move side to side. So we've basically got this almost locked down all the way where we need it to be. All we need to do now is set the rotation motion constraint. To create that constraint, let's go ahead and go up to Constrain, click on the Motion tab, and this is where we can find our two main types of motion constraints. We have our rotation type and our rotation translation. Starting with rotation, let's move over to our selections section, which houses our selection filters so that we can pick up the necessary geometrical elements in our model to create this rotation relationship. Now, starting with this first selection, I want to go ahead and pick up this cylindrical face for this larger gear. And what that's going to do is it's going to pick up that axis there. Now, if I pick up 2 cylindrical faces, so let me go ahead and pick up my second one, it automatically calculates a ratio based on the relative size between those faces. Now, I'd like to note that even though it gives you a calculated solution based on your 2 selections, you don't have to use that. You can just highlight this value and replace it with another value. So in this case, I know that the gear ratio and the setup is a 2-to-1 ratio, meaning that for every 2 revolutions or rotations of this pinion, I get 1 full rotation of this larger gear. Or in other words, for every 1 rotation of this pinion, I get half a rotation of the larger gear. Alternatively, I can also select the faces of my 2 components. So I'll hover over my larger gear and left click, and then I can hover over this face as well and left click. Now I can set a custom ratio as needed for my design. Now, before we move on to the solution section, I want to talk about the pick part first button. So that's this little red cube here in the corner with the checkbox. Normally it's turned off by default. And when it's off, like before, we can go ahead and pick up our geometrical elements directly. But let's say that we have a really complex assembly, or an assembly in which the parts are housed within one another and the element that we want to select is not easily accessible in our default assembly view. So what we can do is we can enable this option, and when we go to make our selections, instead of seeing the highlighted geometrical elements first, we can pick the part of interest first and then pick up those elements second. So let's go ahead and pick up our pinion. So when we hover over that, the entire part turns green. We left click once, and now we can pick up the geometrical element that belongs to this part. So even though I'm hovering over the larger gear, it's not selecting anything on that gear. It's only giving me entries that are available as part of the pinion itself. So let's go ahead and pick up our first face here. And then now we select the second part itself, okay, or that second component itself. And then now we can pick up the specific geometrical element that we want to reference. So we'll select that face, and there we go. Now we can enter our ratio and move on with our next step. Now let's go ahead and reselect our two entries. I want to select the larger gear first and the smaller gear second. And I want to go ahead and change this ratio back to 2. This particular gear ratio is a 2-to-1 ratio, meaning that for every 2 rotations of the pinion, I get 1 full rotation of my first selection, which was my larger gear. Or in other words, for every 1 full rotation of my pinion, I get half a rotation out of the larger gear. Okay. And then now we can move on to our solution section. The solution section allows us to control the direction of rotation between our 2 components with respect to one another. So currently it's set to forward, and forward just means that both of these parts are going to rotate in the same direction. I'll go ahead and demonstrate that. I'll click OK. And let's go down to this angle constraint that we made previously between the XZ plane of the pinion and the XZ plane of the entire assembly itself. So when we right click on this and go to Drive, and hit play, you'll see that the 2 gears move in the same direction. They're both rotating clockwise, okay? But in this particular setup, we don't want these 2 parts to rotate in the same direction. So let's go ahead and correct this. So we'll go ahead and cancel out of Drive, and let's go down to Rotation, right click, and go to Edit. And now we can flip the solution to Reverse. So we'll left click on Reverse and hit OK. Now let's go ahead and drive this constraint. Hit play, and now you'll see the pinion is rotating clockwise while the larger gear is rotating counterclockwise. So that is the correct arrangement for this particular gear setup. Now I want you to note that the teeth between the 2 gears are sort of misaligned in this particular case. So let's go ahead and fix that before we continue on with the lesson. So what I'm going to do is I'm going to create an angle constraint between the XZ plane of the larger gear and the XZ plane of the pinion. Okay, and this will help correct the offset and the teeth. So we'll go to Constraint, Angle, XZ for the large gear, XZ for the pinion, and let's set a directed angle solution with an angle of 4.5 degrees. Now, when I look at the front of these 2 gears, you'll see that the teeth are aligned properly, and I can go ahead and click OK. Now, one thing I'd like to note is that even though this additional angle constraint that we just put in the model fixes the alignment between the teeth of the gears in its initial state, we need to suppress this so that it doesn't conflict with our rotational motion constraint that we put in earlier. So we can right click on this new angle constraint, go down to Suppress, and then we can go ahead and drive this assembly. So let's do that. So we'll right click, go to Drive, we'll click Play. And now you can see that the teeth are meshing together properly. We're getting the correct gear ratio characteristics that we have as part of this design, and everything is functioning as intended. Before we move on to the next example, I wanted to go ahead and point out these little arrows in the bottom right-hand corner of the Edit Constraint window that essentially just expands the menu and gives you access to those additional options that may reside in this menu. So here we can click in this box and give our constraint a custom name so that's easily identifiable within our model browser. This becomes very useful when our assemblies become quite large. In this next example, I went ahead and added a couple gears to our initial example that we just covered. So I'll quickly walk you through the setup of this assembly so that you can understand what's going on here. So starting at the bottom, we have our same pinion that drives everything. So this is the only gear that's actually driving everything in this assembly, okay? And these 2 gears are set up in the same exact fashion that they were set up in the previous example. Then I went ahead and added a shaft that is directly tied to this gear here. So the shaft will rotate at the same rate that this gear rotates. And then on the other end of the shaft, I went ahead and fixed a smaller gear, okay? And this smaller gear rotates at the same rate as the shaft, which rotates at the same rate of this gear here, okay? And then we have this larger gear at the end that is being driven all the way through by this pinion. So As this pinion spins, it'll spin this gear, which spins this shaft and this smaller gear, which will then finally drive this gear at the end that's only constrained by its axis here in 3D space. So it can freely rotate, but it's being driven by everything in this lineup of gears. Now let's go ahead and take a look at the rotational motion constraint that I created. So this is the second rotation motion constraint that's in this assembly that creates a relationship between this smaller gear that's directly tied to this drive shaft, which is tied to this gear. It creates a relationship between that system and this final gear here. So like before, I selected the larger gear, then the smaller gear, set a gear ratio of 4 because this is a 4-to-1 gear ratio. Okay, I put it in the reverse solution option. And when I click OK, it creates that relationship between these two gears exclusively. But because this smaller gear is tied into this one, which is driven off of this pinion underneath it, it drives the entire assembly when we just drive the pinion angle constraint by itself. So let me go ahead and show you what this looks like when this pinion down here is driving everything. Now, the reason why I'm showing you all this is because I wanted to show you a more complex use of a relatively simple command like the rotational motion constraint. Okay, so let's go to the angle that's driving all of this by this pinion. Okay, so we're going to right click on that angle, go to drive, and let's hit play. Now you'll notice down here, this pinion is rotating, which rotates the gear above it in the opposite direction. And everything on this shaft is tied into the same rotation rate and direction, which is driving this final gear back in the opposite direction. So these are two separate angle rotation constraints that are chained together to create this complex set of movements. Moving on to our rotation-translation constraint, what you see here in front of you in this particular example is a rack and pinion setup. So here's our pinion gear. As this rotates, this moves this rack along a linear travel direction, okay? So that is our rotation-translation example. So let's go ahead and start from scratch. I'll show you all of the constraints that I used leading up to the rotation-translation constraint so that you fully understand how I'm setting this up to then apply that constraint. Starting with a blank assembly file, let's go ahead and import our pinion component. So we'll double click on that, drop it anywhere in 3D space, and click OK in our marking menu. Starting with our first constraint, let's go ahead and constrain the central axis with the Z axis that's tied to the assembly. Let that snap into place. And this is able to move along that axis and rotate about that axis. So let's create another constraint. Go up to constrain, and let's go ahead and constrain this rear face on the pinion itself with the, let's see, XY plane of the model and set that to flush. Okay, we'll hit OK there. And now that's locked into place except for the rotation around the Z axis. So now we just need to set an angle constraint between one of the planes for the pinion and one of the planes in the origin. Go to constrain, angle. We want a directed angle solution. And let's go ahead and pick up the XZ plane that's tied to the pinion and the XZ plane that's tied to the origin. We can leave it at 0 degrees and click OK. Now we'll come back and drive that particular angle constraint to create the rotation and translation in this assembly. Next, we need to go ahead and bring in the rack component for this assembly. So we'll go to place and we'll pull in the rack part. Okay, we just drop it anywhere. Go to OK, and let's create some mates to get this directly aligned with the pinion. Let's go to constrain, and then let's go ahead and create a flush constraint between these two faces. So we'll click on this face, we'll click on this face, and then we'll select the flush solution. Okay, and we'll hit OK. Now this part is free to move around in 2 dimensions, but it's locked flush with this front face. So let me turn it sideways. You'll see that it'll move forward and backwards and up and down. So we need to lock it in place up and down first, and then we can worry about this direction here. We'll go to constrain once again, and we're going to set the offset based on this face here and the central axis of this entity. Okay. And let's go ahead and enter our value. I went ahead and found this value ahead of time. Okay, we'll go ahead and click OK. And now when we take a look at this model and slide this over, you'll see that it's able to both rotate around this element and sort of move back and forth. So we need to lock this rotation of the rack. So what we'll do is we'll go back into Constraint and we'll create an angle constraint between this bottom face and the XZ plane that's tied to the origin. So we'll click on that. We'll select directed angle and we'll put a value of 180 degrees there so it gets our orientation correct there. And we'll click OK. Now we can slide this back and forth along that area. So all we need to do now is set up the initial position of this and set up the rotation translation motion constraint. I went ahead and clicked and dragged the rack and got it into an aligned position with this tooth here on the gear. And now all we have to do is create our motion constraint. So let's go up to Constraint. We'll go to the Motion tab, click on Rotation Translation. Our first option is going to be the rotational component. So I'm just going to pick up the central axis here. Okay, and then our second entry is going to be the direction of the linear travel. So you can either pick up the normal off of a face. So you see when I hover over a face, it gives me the normal vector that comes straight off of it, or I can pick up an edge. So in this case, I'll go ahead and pick up an edge. Okay, and then I need to set my linear travel distance for every one rotation of the rotational component. That's what that number is. So let me go ahead and pause here for a moment and show you how we can find this length of linear travel for every one rotation of a circular element. So when you're dealing with a rack and pinion system like this, all you have to do is take the pitch diameter of the pinion and multiply that pitch diameter by pi. And that'll give you your circumference of that pitch diameter, which is the distance that this will travel linearly in your assembly. So for this example, our pinion pitch diameter is 3/4 of an inch or 0.75 inches. So we take that diameter and multiply it by pi. And when we do that, we get a value of 2.356 inches. Okay. So I took the pitch diameter value, which is 0.75 inches, and multiplied that by pi. And so we get this value. So we'll go ahead and copy and paste up to 3 decimal places. That should be more than sufficient. We'll exit out of that. And then we'll set that distance in here. We'll paste it, and now we can select our solution option. On a side note, you can also use this little arrow that's attached to the distance parameter field to measure an element within your assembly and use the length or the measured entity itself as the parameter inside this box. So let's click measure, and let's use this edge length on the edge of this part as our distance measurement. So we can just click on the edge and you'll see it changes it to 6.188 inches. That's the length of this entire edge. So depending on your design intent, you have that option available to you as well. And you can also enter previously entered parameters that the software remembers from the past. Let's go ahead and change this distance back to the correct value and move on to our solution. So we have two main solutions. We have the forward solution and the reverse solution. We'll leave it on forward, see what happens, and then we'll reverse that so you can see the difference between the two. And of course, in your extended menu, you can rename this constraint on the fly if you choose to do so. Let's go ahead and click OK. And now you see we have our rotation translation constraint here in the model browser. So let's go ahead and drive the pinion angle constraint that we created earlier and see what type of motion takes place in our assembly. So let's go ahead and right click on this constraint here. We'll go to drive, and I went ahead and set the end angle to 720 degrees so we can see plenty of rotation take place in this system. So now let's go ahead and press play. Now notice the pinion is rotating clockwise while the rack is moving in the wrong direction for this particular application. So let's go ahead and change this so we get the proper direction of movement. We'll go ahead and right click on rotation translation here in our model browser. We'll go to edit, and let's switch the solution to reverse and click OK. Now let's drive this assembly again and see what happens. So we'll right click on this angle constraint. We'll go to drive, and let's hit play. So now we could see we get proper meshing of the teeth. We have the proper direction of movement for the rack with reference to the pinion. So now let's go ahead and get a better initial starting position and direction of movement for the rack itself for visual representation. So what we're going to do here is we're going to hit cancel, right click, go to drive again, put a negative sign in front of this 720 degree parameter, and let's hit reverse now. So now we are using the full distance of our rack and getting a good visual representation of this rack and pinion system. That's all for this segment of the Autodesk Inventor Assembly Creation module, where I gave you an overview of the motion constraints. I really hope that you found this tutorial to be helpful and that you put what you've learned into practice so you can continue developing your skills as you work your way through these lessons. Also, before you watch the next video in the series, make sure you subscribe to my channel and turn on notifications to stay up to date on future content that will help you create the future you want for yourself. And of course, don't hesitate to leave a comment or reach out via my website contact page and let me know if there's anything else you'd like to learn about or see on this channel. I really appreciate you choosing to stop by and learn with me, and I'll see you again soon.